Hey everyone, I hope you're doing well today. In this video, let's talk about how to find the orthocenter of a triangle given 3 vertices. Jumping right into it, let's find the orthocenter of a triangle with the vertices at each of these following coordinates of 0, 0, 10, 5, and 3, 12. I'm going to go ahead and label each of these points A, B, and C. Here they are plotted on a coordinate plane, and this is them connected to make a triangle. Because all 3 of these angles are less than 90 degrees or are acute, we know this is going to be an acute triangle. When dealing with acute triangles, the orthocenter is always located inside the triangle. Remember, if we had an obtuse triangle, then the orthocenter would be located outside the triangle, and if we had a right triangle, the orthocenter would be located on the actual triangle. Remember, orthocenters are located at the intersection of the altitudes of each of the 3 sides of the triangle. For this particular triangle, if side AB was the base, then the altitude would be perpendicular to side AB but would go through point C. If segment AC was the base, then its altitude would be perpendicular to segment AC and would go through point B. And finally, if segment BC was the base, then its altitude would be perpendicular to it and would go through point A. In order to find out the exact equations for the altitudes, let's start by finding the slope of the segments that make up this triangle. Because vertex A is located at 0, 0, and those are nice numbers to use, I'm going to start with segment AB. Essentially, slope is just rise over run, or the ratio of vertical change to horizontal change. From point A to point B, we have a vertical change of positive 5 units up, and we have a horizontal change of positive 10 units to the right. Simplifying this down, the slope of segment AB is equal to 1/2. Using vertex A again, let's find the slope of segment AC. From point A to point C, we have a vertical change of positive 12 units up, and a horizontal change of positive 3 units to the right. Simplifying down this ratio, we know the slope of segment AC is equal to 4. Now that we know the slopes of these 2 segments, we can go ahead and find out the slopes of the altitudes that are perpendicular to them. Remember, perpendicular lines have opposite reciprocal slopes, so if segment AB has a slope of 1/2, then its altitude is going to have a slope of -2, and if the slope of segment AC is equal to positive 4, then its altitude is going to have a slope of -1/4. Let's go ahead and find out the equation of the altitude that's perpendicular to segment AB but goes through point C, which is 3, 12. While some people prefer to use point-slope form like I do in another video, I'm going to go ahead and use slope-intercept form instead here. Plugging in point C and the slope, we can write 12 is equal to -2 times 3 plus b, and multiplying -2 and 3, we can write 12 is equal to -6 plus b, and then adding 6 to both sides, we find out that b is equal to 18. The equation of the line that contains one of the altitudes is going to be y is equal to -2x plus 18. So here's where segment AB is, and this dashed line represents the equation we just found of y is equal to -2x plus 18. Notice how this dashed line goes through point C, has a slope of -2, and is perpendicular to segment AB. Now let's go ahead and try this process again to find the equation of another altitude so we can draw and find out where they intersect. We'll go ahead and find out the equation of the altitude that's perpendicular to segment AC and goes through vertex B at 10, 5. Again, I'll use slope-intercept form again, and substituting in, we can write 5 is equal to -1/4 times 10 plus b. Multiplying -1/4 and 10 together, we can write 5 is equal to -5/2 plus b, and adding 5/2 to both sides, we find out that b is equal to 15/2. The equation of the altitude that's perpendicular to AC that goes through point B at 10, 5 is going to be this y is equal to -1/4 x plus 15/2. So again, here's where segment AC is. And this dashed line here is represented by the equation we just solved of y is equal to -1/4 x plus 15/2. Notice how it's perpendicular to segment AC, goes through point B, and has a slope of -1/4. This point of intersection where these 2 altitudes meet is called the orthocenter. While their point of intersection seems pretty clear in this diagram, let me show you how to find it out algebraically in case it doesn't. Basically, we're just going to take the 2 equations of the altitudes we just found out and solve them as a system together. Since y is equal to both of these expressions to the right, we can substitute in and write -2x plus 18 is equal to -1/4 x plus 15/2. To get rid of all fractions for this equation, we can multiply the entire equation by the LCD of 4, so if we distribute it, we're going to get -8x plus 72 is equal to negative x plus 30. Adding 8x to both sides, we'll get 72 is equal to 7x plus 30, and subtracting 30 from both sides, we get 42 is equal to 7x. Finally, dividing both sides by 7, we find out that x is equal to 6. So while the x-coordinate for the orthocenter is positive 6, we can go ahead and plug in that 6 into one of these two equations to find out the y-coordinate. I'm going to go ahead and use the top equation since there aren't any fractions. Plugging 6 into this top equation, we'll have y is equal to negative 2 times 6 plus 18, and negative 2 times 6 is negative 12, so we have y is equal to negative 12 plus 18, and negative 12 plus 18 is equal to 6, so we know that y is equal to 6. At this point, we've now confirmed that the orthocenter is located in quadrant 1 at 6, 6. And in case you were wondering, here's where the last altitude would be. It'll go through point A and is perpendicular to segment BC. Remember, even though there are 3 sides of a triangle and 3 different altitudes, we only need 2 of them to find out where the orthocenter is. If you know where 2 of them intersect, then we know where all 3 of them are going to intersect. And there you have it. This is how you find the location of the orthocenter when given 3 vertices of a triangle. If you found this video helpful, please consider subscribing, leaving a thumbs up, and maybe even a nice comment. As always, keep up the great work, and I'll see you in the next one.